Flow rate is an idea that comes straight from volume conservation. This is a video about flow rate. So first, I guess we can define flow rate. Flow rate gets a letter Q. I'm not sure why it's Q, but it's going to be equal to a change in volume over a change in time. Let me show you a couple of ways to do this. If I have a column, and this was all over the last video, is columns. If I have a column and I said I've got a certain amount of water here, and I want to move that water downward, so I'm going to move this water by some height, by some distance h. If I do that, I can say, kind of what I had before, where I had like an A1H1 equals A2H2. But then there are questions. What if I want to move this in a time of 2 seconds? Well, if I divide on the left side by time, I have to divide on the right side by time. And now I've got something that gets a little bit more helpful. A height divided by a time, that looks a whole lot like a speed. And it is. And I've got a height over time here. That looks like a speed. So my flow rate equation I could write as an area times a speed. Now, area is going to give me units of square meters. Speed's going to give me units of meters per second. So this is going to be a cubic meters per second type of quantity, which we already knew here, cubic meters seconds. And what I get is that my flow rate is also a constant quantity. So my area 1 times V1 is going to be equal to my area 2 times V2. Or if you like, Q1 equals Q2. This one seems like it's really logical, and also kind of seems like it might be kind of, where is this coming from? If you are standing, this is where I'm going to show you that you already knew this. If you are standing and you are holding a garden hose, and here is your sibling, well, the garden hose, you're trying to get them, but it doesn't do a whole lot. So what do? Well, the same thing that everyone does. If this is the end of the garden hose, you are going to take your thumb and you're going to cover a whole lot of the end of the garden hose. This is your thumb. So now the water only comes out through this little portion. And when we do that, now we get this. Why does that work? Well, we had a certain flow rate. We turned on the hose and we had a certain flow rate. And that was a constant. What we've done here is we have decreased the area that the water can actually go through. Right? We had the whole area of the circle. Now we've got only this area that the water can go through. If flow rate is going to be an area times the speed, and we drastically decrease the area, then we increase the speed to offset that. So now this water that comes out is going a whole lot faster. There's another example that might be relevant to you. What if instead of a vertical column, we look at a horizontal column for a little bit, and instead of water passing through this, we're going to have blood passing through it. Well, blood has its own flow rate, and if this is like an artery, then we get a certain speed for that blood. what happens when we get like buildup of plaque in that artery is that we have reduced the available area to something a whole lot smaller. If we reduce that to a smaller number, if we reduce our area, we are increasing the speed. And suddenly you see an effect where this has more dire consequences than just getting sprayed with a garden hose. Now we've got a problem. So these are examples of where flow rate comes into play, and all we are saying is that flow rate is an area times the speed, and it's a conserved quantity. That's it.